Bismillahirrahmanirrahim. Starting a new video with the MST algorithms. And so this video is going to have contain the Prim's algorithm, its dry run, its algorithm, and its analysis. So starting with the algorithm, first of all, I will show you the algorithm from the book. The book is Corman's Introduction to Algorithms. So here is the algorithm of Prim's algorithm. This is the initialization for all the vertices, just like the BFS. So the key is equivalent to the distance. So key is infinity, the parent is nil, and this is the key of source, that is 0, and then you have a queue that is currently you have created it with an empty status. For each vertex u belongs to g dot v. It's a loop for all the vertices. Insert q comma u. So you will insert this one into. So you will be inserting all the elements one by one into q. So this part is a little bit different from BFS, because in BFS you insert the values when you explore some vertex, and you insert those neighbors of that vertex into the queue. But here you can see that you have inserted all the vertices in the queue at the very beginning, and then there is a loop while q is not equal to null. So you continue it till the end of the queue, extracting one element from the queue and looking at its adjacents. If v is in the queue, and then you will check the weight of uv. If it is less than the v, then it would be updated, otherwise it would be just skipped. And then if it is updated, then the key of that v would be decrease key, because this is going to be a priority queue is going to be used, so it is decreasing the value of the key. In the dry run, I will be having only this part of the algorithm on my copy, so that we can run the loop. So initialization is already done there. So this is the part. So I was discussing on that I have noted down only the line number 8 to line number 14 on this one, so that I can be execute this part on this graph. For that one, we have just created a cube, and we inserted all the elements, all the vertices in this cube, and so every value of every vertex is the key value of every vertex is infinity. That is marked here. So in this execution, I mark this as infinity at every place, like this one, so that this can be updated during the execution. Okay, in this one we would be having two arrays, that is key and parent. So you should be maintaining this one on your notebooks. So this would be an array with parent and one with key. So this array should be there, so you can maintain it just like we did it in the BFS. So here I will be explaining only how it's going to work. So all changes are going to be can be seen in these arrays. Okay, while q is not null, so we can see the q is still not empty. U is equal to extract min. So here we are going to extract an element. So u, so we are extracting the minimum one, so we will get a from here, because its key was updated to 0. So we extracted a here, extracting minimum. For each v belongs to adjacent of u. So now there are different adjacents of a, so that is b, g, f and e. So let's say we pick first e. So adjacent of U is that is A is E. What next we will need to do, for each V belongs to adjacent of U, so we have picked one first adjacent. If V belongs to V belongs to Q, so V belongs to let's see, yes, V belongs to Q, that is true, and weight of UV is less than weight of key, so weight of weight of UV, so weight of UV is basically the 4. So we mention it like U comma V is equal to 4 here. So weight of AE is 4. So 4 is less than infinity. So that is true. So after this one we will be doing, because this condition is true, so V dot parent is equal to U. V dot parent. So we will marking U as the parent of E. Then what next? V dot key is equal to weight of UV. V dot key, the value of key would be updated to weight of E, so that is decrease key QV W comma weight of UV. So the weight of E is decreased to what? The weight of edge, so that is 4. So it is crossed and the new weight is there, that is 4. So that means the weight of E is now 4. Now going back to this one, next adjacent, that is F, we will mark its parent, and then this infinity is less than 3, so it would be 3, so the F is updated to 3. So the next neighbor we picked was F, and the weight of this one was 3. Okay, so this is done. Now up next we get the next adjacent, that is, let's say G. So this is infinity and this is 2, so it will be replaced with the 2. So next adjacent is G and the weight is 2, so AG. So A is marked as the parent of G, and then we will be going for the next neighbor. So this 8, let's reflect it in the Q also. This one is 2. Next neighbor is B. So next neighbor is B. So B's key is infinity, that is less than 3, so it is updated, and this is marked as the parent. So A is marked as a parent of B. Okay, so the distance of B is updated to 3. No, so that was 3. So is there any other neighbor of this one? So there is no neighbor, so this loop will terminate and this loop will terminate, and it will go back to while this one. While Q is not equal to null, so Q is still not null, it will extract the minimum element from the Q. What is the minimum element? So that there are B, C, so this is 3, infinity, infinity, 4, 3, 2 and infinity. So the minimum element is G. So it's going to extract G. So these are the neighbors of A. Okay. Now for each edge V belongs to adjacent of U. So this is G. So we are going to mark the neighbors of all these ones. So there is a parent, there is a neighbor that is H. So there is a neighbor A. So let's see that what happens with A. So if it is a neighbor, V belongs to Q. Does A belongs to Q? No, it is not now in Q. It was extracted previously. So this condition fails. So if some vertex is already explored, so it's not going to explore again, so we skip it and then go back for the next neighbor. So the next neighbor is, let's say, h, and the distance is, so next neighbor is h, next adjacent. So we will mark its parent and then we'll update its distance, that is 3. We will update, reflect this update into the this queue also, and then we go for the next neighbor. So next neighbor is this one. We will mark g as the parent of c. We will update its key, so that is 2. So now it is 2, and then we will love to reflect this change in the queue also. So this is done. So is there any neighbor of g? So no. So after coming up here, we have explored all its adjacents, so it will move back to the queue. So there were 3 neighbors that are explored in this one. Next we will extract the minimum element and keep it in, place it in u. So there are 3, 2, infinity, 4, 3 and 3. So we will pick 2, that is C. So C is explored like this one. So C is explored. Now we will find all the neighbors of C. So the first neighbor of C is B. So let's pick it B. Then what will happen is distance is 3 and the weight of UV is, so V belongs to Q. So yes, V belongs to Q. So this part is true. Weight of UV is less than weight of the value of key. So its weight of UV is 7 and the value of key is 3. So that means this condition is false. So we will skip this one. So there is no update can be done on this part. So going for the next neighbor, so that is D. Now its distance is infinity and then the weight of UV is 2. So first of all, D is in key, so this is less than more than 2, so it is updated and the parent of D is marked, C will be marked as the parent of D. The next one is this one. So we see that the weight of UV is, so exploring H, weight of UV, that is CH, is 1 and the previous weight of key is 3, so that this one is less than 3, so it is going to be updated. So this is now 1. Previously it was parented by G, so now this part is removed, so it is no more the parent of G, is no more the parent of H, so now the new parent is C. So this is now the parent of H. The next neighbor is G. The next neighbor is G. So the distance is 2 and this distance is, the key of G is 2 and the weight of UV is 2, so it is the same. So there is no need to update this one. So moving towards the next one, so we have I think we have explored all the neighbors of G. So in this way we will be continuing this whole algorithm, and finally we will be having no element in the queue. Now few updates that are missed is done here. So this is 1, this is 2. So next we will be exploring the next element extracting from the queue, that would be H with the cost 1. So now this is H, so this is, that means we are here, and now we will explore all its neighbors one by one and we will see how many uh, adjacents or neighbors are being explored by H. First of all, we see that D is a neighbor of H, but its cost is less than 8, so it is not being explored. So the next neighbor is C, but C is not in the queue. C is not in the queue. The next neighbor is G, so G is also not in the queue, so we'll skip this one. The next neighbor is F, so F is in the queue, but the weight of UV is more than the key of F, so it is not going to be updated. So G, C and F, we are done with this one, and then we will come back to this line and check whether the queue is empty. So queue is not empty, we will extract another element and keep it in U. So the minimum element, so that is there is B with 3, D with 2, E with 4, F with 3, so we will pick D with 2. So we will pick D with the value 2. So that means we are currently here. We will explore our neighbors. So the first neighbor is, let's call it, where is the first neighbor? That is B. First neighbor is B. This one, is B in the queue? Yes, B is in the queue. The weight is 4 and the key is 3, so it's not going to be updated. So the next neighbor is C. We see that it is not in the queue, so we will skip it. The next neighbor is H. So H is not in the queue, so we'll skip it, and then we will go back to the start of this loop while queue is not empty. So case there are still elements in the queue, so we will extract one from the queue, and with the minimum cost, so we have E, F and B, so 3, 4 and 3, so we can pick any 3. So let's say we pick B, so that means we are here picking all the neighbors of B one by one. So first neighbor is A. Okay, what will happen, so is A is not in the queue, so we'll skip it and we'll go for the next neighbor, and that is D. So D is also not in the queue, so we'll go for the next neighbor, that is C. C is also not in the queue, so we'll skip it, and then there is no other neighbor of B, so we will go back to while q is not equal to null. So still there are two elements, one is E and one is F. F is 3, so we will pick the minimum one, that is F. So it means we are right now here. So there are 1, 2, 3 neighbors. So first one is E. So E, so that E is in the queue, so we will check the second part of the condition. So distance cost of 5 is greater than this key, so no need to change this one, it's already in the better situation. So going for the next one, so going for the A is not in the queue, so skipping this one. Then next neighbor is H. Okay, so H is also not in the queue, so we will move back to, so F was extracted. So now we are going to pick the last element, that is E, and we'll put it in the queue. So E is here. Where is E? There are two numbers. One is A, so A is not in the queue, and F is also not in the queue. A and F, they are not in the queue. So now these are the parents, and we can generate an MST from these ones. So we're combining, just looking on the edges that are marked as the parents, so it will be actually stored this in this array. If you maintain this array, you can find that this all the parents will be stored there, and actually this will be generating your tree. So just look, marking at all the edges that are marked with the double lines, so we have this MST. So adding up all the cost on this wedge, we have the MST cost, that is 17. So we can have more than one trees, but the cost of all those MSTs would be 17, not less than that one. So that's how it actually works. Coming towards the analysis of this algorithm, so this is the whole algorithm. So these are the line numbers I forgot to write. So starting with the individual cost of every statement, so it is C1, C2, C3, C4, C5, C6, C7. Okay, so this is not C7, so because this is a function call, so it's, we will mark it. So this is NQ. So this is a function called the cost of NQ, and we are going to use the priority queue, so it would be big of log of V. Okay, so this one is, because q is not equal to null, so we are entering all the vertices once in the queue, and no one, we are not skipping any element from the queue, and every iteration is extracting one element from the queue. So that means it's going to be executed for v times. So it is v7, and it's going to be executed v times. Okay, so this is dq. So then again, the cost of dq would be big of log of v. So for each v, so this is c, let's call it c8, skipping c7, keeping with the line numbers c10, c11, c12, c13, and c14. Now repetition, this is going to be for all the vertices, so it is going to be v times loop, and one time for false, so it is going to be v plus 1, and the body will be executed for all the true execution of the headers, that is v times. So s dot key v is equal to 0, so this is one time repetition, this is one times, for each v belongs to v, so it is a loop for all the vertices, so it is all the vertices, one time for the false, and its body will be executed one time, so that is, it will be executed repeated for v times. Okay, so this is going to be repeated v time. I mentioned that details because every element is inserted into a queue, so it is, and one element is extracted once, so this means this line is going to be executed for all the vertices. So we are extracting, so this line is going to be executed v times, so this is v plus 1, so this is going to be v times, for each v belongs to adjacent of u. If you are using the matrix, then its time complexity would be, its repetition would be v times, and this is inside the loop that is up there in the line number 8, so v times is with that one. So this is only for if you are using matrix representation. And what if you are using not the matrix representation but the adjacency list representation, then it would be something different. We are going to discuss that one afterwards. So, and this is going to be executed at the same time, the same whatever this one is, it will be executed at the same time, and this would be k times, where k ranges from 0 to 1. So k ranges from 0 to 1 times whatever the time complexity that is coming from this part. Okay, now if we are doing it with a matrix, then obviously it's going to be a v square. Okay, so coming towards the total, so what would be this one? So this is going to be v plus 1 in, okay, so so we will be multiplying all these one with a constant individual, so it will become v log of v, and then this will become v, and this will become v log of v, and this will become all the adjacents. So it is v square if we are using matrix representation, and so on. And the decrease key operation is basically v log, this operation is log of v times operation, so it will become whatever the time complexity of these ones. So if these are one v square, then it will become v square log of v, or it would be e log of v if we are using adjacent. Okay, now I will explain what does this line mean. So this is line for all the vertices, and this line is saying all the neighbors of one vertex, that is v. So it means in the next iteration these will be the neighbors of the next vertex, in the next line it will be the neighbor of the next vertex, and one edge generates one neighbor. If there is no edge, then there is no neighbor. Hope you can understand that one. So that means if we combine these two lines like this one, so it is the time complexity of the line number 8, this is the time complexity of line number 10. So if we combine these two, the total effect would be the all the neighbors of all the edges, all the neighbors of all the vertices. So all neighbors of all vertices. So all neighbors of all vertices means not v square if we are using adjacency list representation. So it means e. So not this one. So it will become e. And if it becomes e, so then it means this would be not be wrong, but it should be e log of v. So here you can see that t of v comma e is, so that is c1 into v plus 1 plus c2 into v plus c3 into v plus c4 plus c5 plus c6 into v plus 1 plus v log of v plus v plus 1 c 9 plus v log of v, this one plus e plus c12k e. The value of k will always be less than, or maximum it would be 1. For those who have not attended my previous lectures, c13 k into e plus c14 to k e log of v. So please simplify this one, and you can find there would be two major expression in this one. One would be v log of v, and the other one would be e log of v. So you will find these two major expression in this one, and finally you will get big of e log of v. That is the time complexity for this one using the priority queue. So this was the lecture on Prim's algorithm. Please feel free to discuss anything. You can mark, you can write your comments. You can write your question in the comments section. I can, if required, I will make the video on that one, and otherwise I will be trying to discuss that one in the group or in the comments also. Okay, thank you guys, thank you for listening to me, and thanks a lot. Stay happy, stay blessed, stay safe. Allah Hafiz.